Alright, I'm gonna start this video with a quick heads up. In no way a video would replace a face-to-face interactive lecture, and those who attended the first lecture, whether it's the OS or CA1, they have noticed that we spend a lot of time interacting with each other rather than just reading what is on the slides. That being said, technically speaking, we didn't even get to read what's on the slides because there were so many issues with the computers and the projector, and it was a mess. Anyways, but we got to interact, and that's the most important part. So if you're not sick, if you don't have a force majeure, try and attend the lectures because it's an enriching experience for all. So what I'm gonna do, in order to be fair with everyone, especially those who are tested positive or sick or cannot make it, I'm gonna post a recap. But again, this is not the the important part is the interactive part that we won't be able to do, unfortunately, via the video. I wish we could have used something like Zoom or something like that in order to be able to interact at least online, but unfortunately that's not the case here, and you guys will have to do with the material that's being offered to us here. Alright, so this is lecture number 2. It was lecture number 1, face-to-face. And here we're gonna talk about memory. So the idea was to recap a little bit the different major components of any computer that exists out there. Doesn't really matter to which category it belongs. Every computer has at least those major components, and most of the students were able to correctly identify them and list them back to me, and that was a positive thing. And we decided to focus on first one of the components, which is the memory, and we tried to imagine what are the different things related to memory, and how would memory impact performance, whether it does impact it or not at all. And then we try to see what are the different engineering processes that led into the memory hierarchy that we have in our computers today. Alright, so this is one of the things that I keep on insisting that everyone should, where's my pointer, know by heart by now. So at least we have a storage unit, also known as memory. Then we have the brain of the computer, and then we have the input-output devices, and everything is hooked up together through a bus. And the whole purpose of today's lecture is definitely the storage unit, which is also known as the memory unit. Right, so I tried with the students to imagine using an analogy. Why would I use an analogy where I have a library full of books and some kind of wheel table here, and to map it to the topic of today's lecture. So the idea was to, instead of having all the books sitting on the shelves, well, if someone is interested in a particular topic, that they will bring the books that are relative to that topic and open them up. And we wanted to know why would we do that. And the keyword, the leading thread, the major keyword throughout the computer architecture course and the OS as well, is all about computer performance. So the whole idea is try to enhance performance, and performance is naturally related to something that I exposed in the very first lecture, and the online lecture, the exclusive full online lecture. And that is, performance is equal to execution time. In a way or another, it's 1 over execution time, but performance is all about minimizing execution time, going faster time-wise, right? Clock time-wise. So the idea here still applies in the sense of, well, if I need to access, if I'm interested in astrology, for instance, or astronomy, or whatever the things, hocus pocus things that you are interested in, maybe math. I have no idea. I'm personally not interested in math. We can open all the math books here that are relevant to the things that I want to research, for instance, and then the time to access a particular chapter in a particular book will be way faster than going each and every time, signing up, getting it from the library, and getting it back here. Fair enough. And we try to imagine why would that be faster to have a bunch of books here, related to a particular topic or a particular domain within the mathematical domain, for instance. Well, the whole idea is, it's more likely for me if I read something somewhere that I'm gonna read it again in a way or another sometime soon. Fair enough. And it's more likely for me if I'm reading chapter 9, let's say, of a particular book, it's more likely for me to read chapter 10 or chapter 8, chapter 8, that is, things that are close by. And the same principle applies for the computer memory. So engineers got inspired from that particular analogy here, and they try to implement it in their systems, right? So we don't need to access all books at once. We will be able to find what we want quickly, and this is what we're going to call the principle of locality. I'm going to develop it in the next slide when it comes to computer memory. Alright, so memory and performance, this is a big question. Oh, by the way, I insist, this is maybe not a funny meme. It is a meme, but there's a message that I'm trying to convey using that meme. It's the fact that, no, you don't need to memorize like a parrot. I know. Again, I said it to my face-to-face students. I'm gonna say it for the ones who did not attend the lectures. Parroting does not work with my courses. It doesn't work like that. So you're gonna see that I'm gonna make you use your future engineering skills, and I'm gonna help you out build your engineering skills. This is the whole point of it. All right. So do not expect what you're seeing in the lectures. You'll be seeing it again in the tutorials, and then again with different values in the exams. It doesn't work like that. I'm here to challenge your engineering mind. So yeah, back to memory and performance. So you can, if you want to try and simulate the fact that you're having some kind of interaction, you can pause the video, try to answer the questions, and then resume it. So yeah, what do you think? Is there a relationship between memory and performance? Well, the obvious answer is yes, because first off, we've seen in the first two lectures, whether it's the OS or the the CA one, that the CPU is extremely fast compared to the other hardware components of a computer. So this is why some other components have buffers, for instance, to keep up with the CPU. So yeah, if memory is slower, and especially memory is way slower than the CPU, memory access slower than the CPU. So the ideally, I want to try and keep up with the CPU in a way or another. So I'm gonna try and engineer a system that will be able to keep up with the CPU. The question is, what kind of memory do we want to have when it comes to computers? Well, ideally, again, from a purely theoretical point of view, it would be awesome if we could have infinite access to all the elements instantly, like fast, right away, anything that I need. But of course, because of the laws of physics, this is impossible, and this is what we're gonna, try and engineer it. So yeah, memories are definitely critical to performance, and ideally, as I said, I need indefinitely large memory capacity with fast access time, right? So all I need is, whenever the CPU will be asking something, because remember, inside the CPU I'll be executing instructions, and the instructions are they're always stored in the memory. Fair enough? So whether it's instructions or data, but I'm gonna focus on data for now. So if I need some data from the memory, I need it right now. Right? So ideally, it would be awesome if I could have immediately available data, whatever, each and every time I try to solicitate and try to take the data. Alright, so in order to have that, so we're gonna try and fake it to make it. as engineers, we're going to use the principle of locality that we've learned from the analogy from before and try to apply it to the memory system. So check this out. So I'm going to introduce temporal locality, and this is exactly the same thing that I talked about earlier. If something in the memory is being referenced, so most probably I'll be referencing it again real soon. Let me explain that. So if your program is trying to access a value of variable a, maybe it's going to change it, maybe it's going to read it, whatever, right? There's a high probability that it will try to access it again, maybe through a loop, a for loop, maybe through something else. Anyways, so there's a high chance that I'll be accessing something again soon that I'm actually currently accessing. Fair enough? So this is the temporal locality, and then we'll have spatial locality. This one means that if I'm trying to access something in the memory, most probably I'm going to go ahead and access something that is around it. Fair enough? And one of the examples that we try to imagine throughout the lecture with your fellow colleagues who attended, where's my pen? So we said, I asked him, think about the structure, you've done that whenever you program the struct. Think about structure that is very that uses the spatial locality, and some of them correctly answered an array in the sense of an array is made of cells, and those cells are stored in memory. So most probably if I'm accessing the first cell, I'm going to go ahead and access any of the cells that are adjacent to that particular one, maybe through a for loop, maybe I'm trying to do some sorting, something like that. Fair enough? Next. Alright, so in class we talked about the different memory hierarchy, and I made someone try and imagine and explain the different levels here. So they correctly answered that the registers are used to store some kind of data, some kind of information or data, and usually it's rather small because these are, as you've done it in the what do you call it, DSD. In the DSD, you've created registers using flip-flops and stuff like that. So usually they're extremely small. All right. However, the good things about registers is it's their proximity to the CPU. So the registers are actually considered to be inside the CPU, and they are inside the CPU. Fair enough? So they're really close. Whenever I need to execute something or get something, the first thing that I will be using are the information that is inside the registers within me as a CPU. Fair enough? So this is the registers, and then we try to find out what is cache, and the origin of the name, which is stemming from French caché, which roughly means to hide. So the whole idea is to hide the different layers here, in order to make it as if everything is available to the CPU. That's the whole point of it. Alright, and we said that most probably if we follow the same approach, that registers are extremely close to the CPU, and cache is really the first official memory level that is outside the CPU. Newer architectures, they do have some level of the cache inside the CPU as well, but I don't want to go there. It's too early for you guys. Maybe you're going to see it in the microprocessor course next year. Alright, so here you can notice that the cache is also divided into different levels, hence we can have different levels of cache. But again, this is not something that I want to cover this year. And then comes main memory, and you can notice that size-wise it's getting bigger, right? It's however getting further, far from the CPU. And then we can have secondary storage. This could be the disks, etc., etc. So I tried to let them imagine what happens here. So the more we go this way, what would happen, and the more we go that way, what would happen. Let me erase that and do it in a proper way. All right, ali. All right, so maybe that's enough. So yeah, so here it's the closer I am to the CPU, the faster the things happen. So the memories are, the storage devices or the storage units or modules, it doesn't really matter. I mean, the storage entity that I'm using is extremely faster. However, it comes at a price. It's costlier. Fair enough. And this is speed and cost, and then where's my pointer? And then on the other side, well, we have the size. All right, the bigger, the farther, the bigger, and the less costly, the cheaper. However, it is slower. All right, so it's all about trade-offs, and this is, oh, by the way, this is one of the key messages that I tried to convey throughout my face-to-face lectures. It's always, engineering is all about trade-offs. All right, there's no one way to do stuff. There are always multiple solutions for a problem or an issue or whatever, right, for an engineering device. However, you always need to take into consideration the whole context, the application, the budget, so many things. It's all about trade-offs. Fair enough. This brings me to my question. Let's see if registers are the fastest, or let me stick to the cache as well. All right, why not like use a lot of cache and do away with the main memory and the secondary storage, like from theoretical point of view? Well, from a theoretical point of view, nothing keeps me from doing that. However, if I want to stay pragmatic and see what happens in the industry, well, in the industry they have budgets. So basically, if you want to do your system out of those two, well, you're gonna pay a lot, and then you'll end up with computers costing more than 50,000 euros, whether you can buy them today for around 2,000 euros, right? So it's all about marketing and stuff like that. Right, so yeah, I asked the curious people if they ever seen something like that, and some of you guys did actually open up their computers and they've seen the RAMs. Alright, so this is usually what is used as main memory. Alright, and we have different types of memory. So SRAM technology, DRAM technology. So SRAM technology is extremely fast but very costly. So most probably I'm going to use SRAM for what? Most definitely I'm going to use it for the registers, and most probably I'm going to use it for the SRAM, for the cache, right? DRAM is fast, but not as fast as the SRAM. However, it's really not costly at all. I mean, cheap compared to the SRAM. So most probably I'm going to use it to main memory, right? And the disks by nature, they're here as a secondary storage. So secondary storage is everything, like a hard drive, hard disk, something that is extremely big and extremely slow. All right. Then I made someone to notice those things. So yeah, go ahead, pause the video and try to read the different comparisons that we have here, and notice that how much a gigabyte used to cost back in the days in 65. Using the DRAM technology, and you can see it's $2.6 billion. So you can imagine you could have like bought castles, maybe farms. I don't know. That's the dream, right? Yeah, for a price of a USB stick today. So yeah, for a 1 gigabyte, that's crazy. For the price of, for the thing that you would have bought with the price of a USB stick today. And you can see in 2007 it's really closer to, it's extremely cheap compared to what we have, $5. That's a Big Mac. Yeah, and you can see in 66 the hard drive. So if you wanted to buy external disk or just a hard disk, it would have cost you per giga $1.05 million. So yeah, crazy. And today it's next to nothing. It's almost $0, almost. All right, and here you can see the different technology, the NAND flash drive that everyone is using today. Okay, right here I made them. Yeah, so this is where I asked a couple of students which is better, SRAM or DRAM. So some of them said SRAM, some of them said DRAM, and the correct answer is better compared to what? With what constraints? In what context? So there's always a trade-off. As engineers, your answer should be, we need more information, about whether we have unlimited budget or we have constraints when it's come only strictly to speed, etc., etc. Because the answer will depend on the additional information that we have. And this is why you need to read the questions in your exams really carefully, because I'll be giving you a couple of things relative to the expected answer. So yeah, you can see that this one is faster, this one is slower, so this one beats that one here. This one is smaller, this one is larger. So what is that a good thing to have a small or a large one? So maybe small, because you remember we need to fit them all on a motherboard, well, on a chip, then on a motherboard, right? Expensive, so this is relative to the cost, etc., etc. You can read it on your own, it's not a problem. However, yeah, I made people try and understand what's going on in here. How come this one consumes a lot of power? So yeah, at the beginning it's cheap, but then again, if it's going to cost me too much with power, so maybe after all the advantage is not there anymore. But the question is, why does it consume a lot of power here? And after some time of reflection, some people noticed that it uses capacitors, and by nature capacitors, whenever they're not powered in a way or another, they start discharging, and then this is why you need to feed them voltage to keep them from discharging, right? So there's some power leakage. Yeah, charge leakage because of the capacitors. Unlike this one here, there are no only transistors and latches, so we're good. All right, so this is typically what I would ask you during your exam, something that you've never seen before. Try to analyze it and answer some questions relative to it. Alright, so yeah, check this out. Yeah, from now on, whenever you're gonna speak in terms of memory, whatever level of memory, we're gonna speak in terms of blocks. Alright, so a block is something, the smallest units of information that might be present or not present in a cache or in the main memory or whatever. Alright, so my question is, and this is why I asked your fellow students, so this is the CPU. Most probably, what is this level? So we're seeing two different levels here. So they guessed it correctly. It is the cache, because it's the closest to the CPU. The registers are somewhere around here. Alright, so most probably, what is that one? Most probably, according to the information that we had, some of them answered correctly the main memory. Right. However, even if I'm not tackling it in that particular course, you can have an additional level of cache memory, but again, this is not the purpose of this course. All right, so what is the whole idea? The whole idea is the CPU needs some data, right? It's going to look for it where exactly first? I mean, something that is not already in its registers. So I'm gonna go and look for it in memory. Which level of memory? The closest thing to me, which is the cache memory. Fair enough? If it's there, good for me. If it's not there, I'm gonna go and fetch it from the second level. All right, and then copy it here and get it back here. So yeah, question: if I'm looking for some data and it's there, it's present, right? What is it? What would I call that? We're gonna call it a hit from now. A hit. And if we're looking for something that's not there, we're gonna call it a miss. Fair enough? So the whole idea is to study the hit and miss rate. All right, so something is there, it's found or not found. In order to improve performance, what should we improve? Is it the hit or the miss rate? So we need to improve the hit rate and do away with the miss rate, minimize the miss rate. Fair enough? So let's see. Hit time is the access, get the things that I need and use it. Miss time, if I didn't get it, miss penalty, if I didn't find it here, well, I need to go ahead and fetch it from n+1 here and put it here and use it. This includes access the block, of course, higher level, transmit it through the different levels, using it, copying it, and then using it. Fair enough? So these are the things that you need to master by now. Alright, and one of the big questions that I asked the students to reflect on is, how big should the block be? The block size. So the block is the smallest unit of information that I'll be looking for in a memory. So how big should it be? So some of them, we spend a lot of time thinking about that. So if we have extremely small blocks, this means that we're not respecting spatial locality, in the sense of, well, if my smallest extreme block, most probably I'm going to need the things that is next to it. However, I didn't copy the thing next to it because it's very small. So I'm not, benefiting. It's not a positive thing, because I'm not, benefiting from the spatial locality. So maybe it's a good idea to make my blocks bigger. Maybe. To lower the miss rate. However, comes to think about it, I wish it was this simple, but then again, engineering is all about trade-offs. So the bigger the blocks, the less the chances that I will have, other elements inside the cache. How come? Because my cache is limited in size. So if my blocks are extremely small, occupy most of it. So I'm just left with almost no place at all for other, blocks, for maybe other parts of the programs or other variables that I might be needing later. So it's a trade-off. Again, it's something that we need to experiment with in order to determine this block size. And you can notice that spatial locality is good when we go bigger, so we're respecting it. However, larger means that less number of entries in the cache, and then there will be some kind of competition. So engineers, scientists experimented with the ideal block size. So we can see here the miss rate versus the block size, and here you can see the miss rate and the block size. Right, so we are extremely we have three lines here. It doesn't really matter for now. I'm going to talk about that in a second. So we can see here that if the block is extremely small, next to 0, well, of course, naturally we'll have a huge miss rate. And then the bigger it gets, the lower the miss rate. But comes a time when the miss rate goes up again. Alright, so you can see that we cannot grow our block size indefinitely. Well, they should be somewhere around this area. And this is how we interpret this particular graph. And the question that I asked the students, and this is maybe important for you to know of for sure. So what are the lines? What are the curves here? So the curves here, green, orange, and blue. So you can see here that block sizes are things in memory, and cache memory to be more specific. And the things that I'm looking for are some data required by what? Some kind of instructions executing where? In the CPU. But these instructions are defined by whom? Well, they are defined inside of a program that is, written by a coder or a programmer. Fair enough. So in order to be able to compare computers or whatever, systems, we need to use different programs or the same programs. So the whole idea is try to compare bananas with bananas and apples with apples. Fair enough. So if you want to compare the performance of your computer to your friend's computer, well, you're not going to play a game on it and then your friend will be watching videos. It doesn't make any sense. You need both of you to try to test the same game on the different computers in order to draw conclusions. Here's the same thing. So we're using what we call a benchmark programs in order to be able to compare. Fair enough? Alright, one last thing before we leave here. If we go big as well, it will take more time, of course, because it has more bits, so it will take more. It really depends on the bus, the speed of the bus, but it will take, generally speaking, it will take more time to fetch it between the different levels. Alright, so here trying to define the things that I talked about earlier. So a cache is the first thing that the CPU sees when it comes to memory hierarchy, and it's in between the CPU and main memory. So it's that level between the two. Now I asked someone to try and understand the scenario that happened here, knowing what you know now. So apparently we have cache before, cache after, and if we compare the two, we feel that there's something in red here that wasn't here. So what did happen? So someone correctly answered that apparently we needed some data. Well, a word is a block for now. I mean, we can say that the block size is a word for now. It doesn't really matter. So we needed some data that it wasn't in the cache, and then we experimented a hit or a miss. So we experimented a miss, and we needed to fetch it from the main memory and then copy it in the cache and then give it to the CPU as well. So the cache after now, it has the data that I needed before, in case that I will need it later. So the next time the CPU will try, go ahead and get this thing in red. Well, it's already in the cache now. Fair enough. And we had some trouble trying to guess what those are, and finally someone notice that these are addresses. So everything in the memory is organized in addresses. So we're gonna say that the word, if the word is in cache address number 1 is there or not. So basically we're gonna go ahead and check the address in order to find out if it's there or not. All right. This is what has been said. Now I need to find out, well, the big answer, the big question here is, well, how does the CPU know that if a word is there or not? So some people suggested that we go through all the lines, but remember, this is problematic. How come? Well, it's problematic because if we go through all the lines, well, we're losing a lot of time. This means that we're losing time, less execution time, bigger execution time, longer execution time, hence less performance. Voila. So we don't need that to happen. So there must be some way in order to make that happen in an efficient way. And there's not only one single array, but I mean there are different trade-offs. And we're gonna start with the first one, and then I'm gonna leave it for the next lecture for the other two. All right. So this is what we call direct map caches, and then I let the students try to understand what level is that and what level is that, although it's in the name here. But I mean, I needed them to tell, even if it didn't have the name, we didn't have the names here, how would they have guessed that this is the main memory and this is the cache? Well, because of the size, right? You remember, cache smaller than main. All right. So yeah, the whole idea here is that we have different blocks in my main memory with the different corresponding addresses, and then apparently, according to the schematic that we have here, it seems that this block or that block, that one and that one, the gray ones, they all belong to that particular block in the cache. So the whole idea is, well, hold on. If the CPU is going to look for any of those gray blocks here, it's going to look for it only here, exclusively here. If it's not here, it means it's nowhere to be. It will be nowhere to be found in the cache. It's not in the cache. Fair enough. So this is direct map cache. This is one of the mechanisms that are implemented out there. Fair enough. And then I asked them to try and see what do all those blocks have in common and how come they come here. So someone has noticed, many of them have noticed that the 3 bits that we have here, they have it in common, and those 3 bits 001, right, they correspond to the address 001 here. So it feels like each and every block that ends up with 001, right, it's meant to be here. So let's verify if it's true by using the second blue block here. So apparently the blocks ending up with 101, 101, 101, and 101, they are all belonging to that particular block. So hence, if the CPU is looking for the block with the address, with the memory address 00101, it will look for it in the cache and the cache address 101. And we call it an index, but we're gonna get to that. Fair enough. So let's see. This is block number 1, decimal 1. This is block number 9, decimal 9. This is block number, let's see, 17, decimal 17, and this is block number 25, decimal 25. So the question is, what's mathematical equation would let the CPU know where to find it in the cache? So what's the relationship between those here and the address here, the index here? Let's call it the address for now. Well, someone noticed that, and good for them, that 1 modulus 1 is 1 modulus 8 is 1, and this is the size of the cache here, right? 9 modulo 8 is 1, again here correctly. 17 modulo 8 is 1 as well, and 25 modulo 8 is 1 as well. So see, the mathematical formula to use is the block address, so the address that we're looking for in the memory, modulo whatever the number of blocks I have in the cache. So if it's an 8 block cache, so I'm gonna be making model 8, and then I'll be determining that thing. Take 5 minutes to test it with the blue ones on your own. Alright, now the last thing that I didn't get to do with everyone during class, but I'm gonna just introduce it here for the sake of it. The whole idea is this particular place is shared between all those blocks. So there could be any block in that particular place, right? Not necessarily the one that I'm looking for, the CPU is looking for. Fair enough. So it could be block number 1 or 9 or whatever, right? How would I know that it's the thing that I need? So, oh yeah, right. So I did introduce it in the face-to-face lecture, and someone told me that why not just give it some extra information? But then again, this means that I'm trying to make the hardware more complex, and maybe I'll be losing more time. Why not use something that's already there? And then someone noticed that, hold on, it's true that the suffix here, the 3 bits 001, 001, 001 are the same. However, the first two, they always change. See, 00, 01, 10, 11. So maybe it's a good idea to go ahead and check the first 2 bits. Fair enough. So the suffix is used as an index, and the prefix is used in a way or another to determine if it's the word that I'm looking for or the block I'm looking for or not. Fair enough. Check this out. So this is what we have, and we're gonna try and divide it into 2 things. The index that I talked about, that doesn't change, and then the tag is the thing that changes between the different blocks. Hence, if a block is present in the cache, I'm going to go ahead and check the tag if it corresponds to the tag of the block that I'm looking for. And then, just again, because I'm obsessed with performance, and performance is all about going faster, so the whole idea is to add 1 single bit, right, in order to know whether there's something in the block, in the cache block, or not at all. This will avoid, the mechanism of going through the reading the tag and reading the what do we call it, the index. It will be just reading the tag. It will be just, well, if there's something, let's go check if it's the correct one. If the valid bit is off, it's 0, this means that there's nothing. It's not even worth it to look inside the particular fields. Alright, so you can see it this way. Well, this is not technically correct because the tag is part of the address, and then I have an extra bit. So let me correct that in a way or another. It should be easier. So this one is still the tag, and then my valid bit is here. Valid bit, voila. Way better. Right, fair enough. So the index is what we're gonna see inside the cache. This is the addresses of the cache, and the tag is the things that is different between the blocks that might be in the tag, so I can correctly identify if it's the block that I need or another block that is supposed to be here. So that's it for this lecture. Hope to see you all face to face. If not possible, hope to be able to maybe someone trying to get administration to use Zoom or something like that, because it would be interesting to interact. All right, have a nice one. Bye bye.